and we are gonna continue with the paper locating other sources with geometric syntactic genetic programming. I have seen João Macedo and Ernesto Costa, so I don't know if some of you are gonna do the presentation maybe. So João?
Yes, can you hear me?
Yeah, perfectly, thank you.
Okay, so I'll do the presentation. Hold on.
Okay, it looks good. Yeah.
Does it look good?
Yeah.
Okay, because it's kind of weird on my side.
Okay.
But okay, I'll start presenting like this. So good morning, everyone. My name is João Macedo, and I'm here to present to you this work entitled Locating Other Sources with Geometric Syntactic Genetic Programming. This work was conducted at University of Coimbra under the supervision of professors Lino Marques and Ernesto Costa. So in the first place, why are we interested in locating other sources? Well, smells enables us to locate distant targets, even if they are silent and invisible. Animals use smells to locate things such as food, detect danger and other mates. But we can use it to locate victims trapped under rubble or detecting illegal substances such as drugs or explosives. Up to now, we have been using trained dogs to help us with these tasks, as our noses are not sensitive enough to do them by ourselves. But the dangerous conditions that are typically associated with these tasks motivate us to replace the dogs by robots that should have high degrees of autonomy and could be monitored from safe distances. Unfortunately, locating other sources is not an easy task, as the other particles flow with the wind and spread through molecular diffusion and turbulent dispersion. The resulting chemical plumes, which you can see in this video, are intermittent, meaning that they contain local voids of concentration and peaks, which hamper our ability to estimate concentration gradients and follow them to the source. Also, the process of locating another source has three well-defined stages. In the first stage, the robot would start and have to explore the environment looking for the initial odor detections. In the second stage, the robot will have to follow the chemical information and also information from the wind, use information from the wind to get close to the region of the other source. And in the third stage, the robot would have to pinpoint the location of the other source. Most works in the literature assume that once the robot is close enough to the source, it can identify it with other sensors, such as cameras, and thus focus only on the first two stages. Here, we also make this assumption. So given the difficulty that arises from the natural phenomena of odor dispersion and airflow, and also the rather complex search process that has three stages that do not necessarily occur chronologically, we propose to use genetic programming to evolve the search strategies, as it's not easy to hand design them, and those that exist typically are inefficient in natural conditions. So, sorry. But we are not interested in just using any GP algorithm. As you know, the standard GP typically suffers from bloat, which is the uncontrolled growth of the trees without the corresponding increase in performance. And we would like to be able to visually analyze the search strategies that we evolve for the robots. As a result, we are going to use geometric syntactic genetic programming, or as I shall refer to it from now on, GSYN-GP. This differs from the traditional GP algorithm, as it does a geometric crossover in the syntactic space, rather than just switching subtrees. And I'll just now briefly explain how this crossover operator works. It's done in 3 steps. The first step you'd get two parent trees and convert them into linear representations in pre-order. These two trees are not these symbols are not the ones that we use for our evolution. They are from the Santa Fe and Trail problem, just to make matters easier to understand. So in the second step, you would use the longest common subsequence to produce two modification masks, MA for parent A and MB for parent B. These masks contain the aligned genetic material that is common to both parents, in this case, progn and move, here in gray, and also contains the nodes that should be deleted from parent A to make it more similar to B, and also those that should be inserted from B into A. The third step is just simply creating the offspring, which can be done by either deleting a terminal and a non-terminal symbol, inserting a terminal and a non-terminal symbol, or deleting a symbol and inserting another of the same type, not necessarily in the same position. So in this case, we created two offsprings, the first one by removing if for the head and move, and the second one by removing if for the head and inserting progn in its place. If we wanted to generate individuals at different distances, rather than just making one iteration, we could use O1 in place of A or O2 in place of A, and do another iteration where you would have an individual at distance 2 from the first parent, and so on. So this was the already proposed algorithm. In this paper, we wanted to, rather than just have motions such as move or left or right, we would like to be able to let the evolutionary process to parameterize the behaviors. And also we have more complex behaviors, such as a zigzag motion, which has a direction, a distance for each segment, offsets, and so on. So for applying the geometric crossover, we can have those three operations: deleting two symbols, which is not a problem here. Inserting two symbols is also not a problem. But if we want to delete a symbol and insert another of the same type, we would like to have intermediate steps rather than just replacing the whole symbols. This is what we address here in this slide. Consider that you have two symbols, the one to be deleted, which is ND here, and the one to be inserted, which is NI here. What we propose is to create a new node, NN, with the main symbol from NI, the one to be inserted, and also to directly copy all parameters from NI that are not present in ND. Those that are only present in ND and not in NI are not going to be useful, so they are just ignored. Then we have to address the parameters that are common to both nodes. We start with those that take numerical values and just average them and use the resulting value for the new node. And for those that take non-numerical values, what we did was we randomly selected k parameters to be copied or to take the values from Ni and use the remaining parameters from Nd. In this case, there was only one parameter left, so the termination criteria here in yellow is copied directly from the node to be inserted into the new node. Then the crossover operator would just insert NN in the place where it was supposed to be to create a valid individual. So having extended GSynGP, what we wanted to know is if it could evolve such strategies that were at least competitive to those of the literature, and and how do they compare to those evolved by the standard GP algorithm. As we know, ER experiments are traditionally slow, so we did all the evolutionary process in simulation and just used the best strategies evolved for real-world validation. This is a screenshot of the simulator that we used. It was developed by us in a previous work. It has the advantage of being quite fast. In its current version, it's running roughly 4,000 times faster than real time. And it uses realistic models for the Odour dispersion and the airflow. The other is based on filaments. The other model is based on filaments. And the airflow is these black vectors, which are computed in a grid through a set of partial differential equations. And a random Gaussian noise is then added to emulate the effects of turbulence. So we got two strategies from the literature. One of them is inspired by the behavior of the dung beetle. Another one is inspired by the behavior of the male silkworm moth. These strategies were coded using the same symbols that were in the terminal and function set. And as a result, they also had parameters that needed to be optimized. And so we used a 1+1 version of the GP algorithm that relied only on parameter mutation to find the best variance. We then have the two population-based GP algorithms, SGP, which is a sub-tree crossover, and the extended version of GSynGP, which uses the geometric crossover that I explained with only one iteration. Both of them use parameter mutation and also main symbol mutation. One of the first issues that we encountered when we were doing the preliminary experimentation was that we saw that it was possible that a bad solution attained a good fitness value due to chance. Even a random walk could stumble upon the other source just by chance and attain a good value. And the inverse was also possible. So a good strategy could miss the other plume due to its intermittency and attain a poor value. Another issue that we found was that it was not easy to accurately match the Odour and airflow conditions in simulation and in the real world, even though we have a wind tunnel that I'll present in a few slides, but it was hard to accurately match them. So we wanted to have an evaluation mechanism that gives us, on one hand, some assurances that the fitness value is representative of the solution's quality, and on the other hand, that the strategies evolved are reasonably robust to various environmental conditions. So what we did was we devised three different environments that different from each other in the environmental conditions only. The arenas are the same. And we evaluated each solution in those three environments and used the mean value of their performance as the fitness value. So, as I said, the environments differ only in three environmental conditions: the wind speed, the angular variability of the wind, which is basically the standard deviation of the Gaussian noise that emulates turbulence, and the rate at which the filaments are emitted. The first environment is just a slowly spreading plume with no voids. The second environment is a faster plume with some voids, even though it has more filaments, but the wind pushes them before they have the opportunity to spread. And the third environment is a plume with less voids than the second one, but still has some, and more filaments that are spreaded more in the environment. So we performed 30 independent runs for the four algorithms and present here the mean fitness and also the size measured as number of nodes of the best individuals. I forgot to mention that this is a minimization problem. And so, as you can see, GSynGP was attained the lowest mean fitness and also the most stable one, as it has the lowest standard deviation. More interestingly, it produced much smaller strategies than the SGP on average, as it had on average 9 nodes versus 26. And those strategies can be considered to have appropriate sizes, as the dung beetle is coded in 5 nodes and the silkworm moth is coded in 15 nodes. So we then apply the Wilcoxon test to the results of the fitness value and use the Bonferroni correction to adjust the significance value. We can conclude that GSIN-GP significantly outperforms the silkworm moth and dung beetle, and SGP is never significantly different from any other algorithm. So the reduction in size of the strategies evolved by GSIN-GP does not produce a loss of performance over those of SGP. Moreover, the size of the strategies evolved by GSIN-GP are significantly smaller than those of SGP, with a p-value of 0.0. So we then took the best strategy evolved by each of the algorithms and performed 5 trials in the real world. Each trial lasted up to 10 minutes, and we considered that an evaluation was successful if the robot could get closer than 25 centimeters from the other source, or on the other hand, it was unsuccessful if the time limit is reached or the robot loses contact with the other plume for longer than 60 seconds after having initially detected odor. This is the mobile robot that we used for the validation. It is an in-house built 2-wheel differential unit. It has also a wind vane here at the top, which we devised in-house. Has a high-level board for acquiring the signals from the sensors and performing Wi-Fi communication, a gas sensor here, 2 proximity sensors, and a low-level board for performing motion control. This is the arena that we use in the simulation. It measures 4 by 3 meters and 50 centimeters of height. There is a set of fans here on this wall that create the airflow. The odor is released here, and this circle demarks the go region where we consider that the experiment was successful. The robot here in the picture is here, but this is not the start location. Here the robot was already performing its search and was already tracking the plume to its source. So we measured the time that the robot needed to search and track the other plume, and also the success rate of the various strategies. The best strategy evolved by GSIN-GP and silkworm moth had perfect success rates, whereas SGP and DB failed 1 of the 5 trials. Also, oddly enough, the silkworm moth was the fastest one here, even though it had worse results in simulation, and GSIN-GP was the second best. The best strategy evolved by SGP was the slowest, both to search and track the other plume. So to sum up, we extended GSIN-GP to be able to evolve expression trees with various symbols per node. We applied that version of GSIN-GP to evolve search strategies for other source localization, and were able to get smaller trees than SGP with equivalent performance. Moreover, GSIN-GP was able to outperform the 2 strategies from the literature, whereas SGP could only match their performance. In the real world, validation, both GSIN-GP and the silkworm moth managed to always locate the other source, while DB and SGP failed 20% of the trials. The silkworm moth was the fastest to find and track the plume, followed by the geometric version of GP, whereas the standard version required the most time. In the future, we would like to explore methods to encourage the behavioral diversity to counteract some premature convergence that we saw in the evolutionary process. We'd also like to encourage the evolution of strategies that attempt to re-encounter the other plume rather than simply halting the motion. This was also something that we saw. Many strategies would get close to the other plume, would just get close to the other source, stop detecting Odour, and would stop rather than attempting to re-encounter the plume. And we would also like to explore ways to quantify and reduce the reality gap so that things such as having the best results in simulation wouldn't and worse results in the real world would not tend to happen so much. So this is just a reference for the simulator that we used, and thanks for your attention.
Thank you so much, João. Thank you, very nice presentation. I think we have time maybe for a couple of questions. Okay. So I leave to the audience. You can either write it in the chat. So Bilandom is asking, how big is the test arena in meters?
The validation or simulation?
In real. I mean,
real?
How big is the test arena in real, in meters?
Okay.
And then a second question, why just 5 trials?
The second question is easy because it takes time. So each trial lasted up to 10 minutes. We had 4 strategies, so it was 50 minutes per strategy, and we had to be charging batteries and replacing batteries in the meantime. So that's the question for only 5 trials in the real world. And is also the reason why we didn't do all the evolution in the real world. The test arena is 4 meters in length by 3 meters in width and 50 centimeters high.
Okay, I think, well, I think, yeah. Bill says thanks. So I don't know if there is still one more question, maybe. Someone? You can unmute your microphone if you like and post the question directly. Okay, João, I think that's all then. So thank you so much again for your nice presentation.
Okay,
and,
thank you.
And I would like to remind you all that, well, 2 things actually. Every presentation you have available a poster room that I'm gonna just here in the chat, I'm gonna paste the link. So for presenters that want to make themselves available at the room, you may know where they're in the link. So potentially you can keep discussing if you are interested in a particular paper from today at 6 p.m. if I'm not wrong. And then the second thing is that today in Evo Apps, we have in the next session, starting at 2:15, so roughly in 1 hour, we have a session with the best paper nominees. So that will be from here in 1 hour, roughly. So thank you so much again for your attention. And well, that's all for this session. Thank you.